Hello again, welcome to Structural Analysis and Design Made Fun and Easy. This is Structural Steelwork Design to BS5950 brace short column. Wow, it's not, I don't know if that's an official description, but this is a brace short column. This is the most simple case, very simple just to get started. Concentric axial load. So this is part 2 of 4 of a series of videos. The other one, part 1, was just to do with the load combinations, the highest compression load and the highest tension load. This is part 2 of 4. Please like the video and subscribe to the channel. Please donate if you can to let me make more videos like this. So yeah, in the previous video I did table of the loads, description of the loading, concentric loading, little diagram of the section. So now we're and then that was part A, maximum compression combination. B was maximum tension load combination. So this is now part C. Check whether this UC section will buckle locally. So in terms of the exam technique, there's 3 marks allowable for this question. So 3 times 1.8 is equal to 3 plus 3 times 8 over 10. 3 times 8 is 24, divided by 10 is 2.4. So it's 3 plus 2.4 divided equals 5.4 min. This is about checking the column section dimensional properties, the ratios of the flanges and the webs to the depth and breadth of the section. So here I've just gone through the main things. This is a cross section of the column. The flanges are done in blue, the webs in purple. So this is y axis as well. In this question, this is x axis. So this is the major axis, because bending about x is about the strongest ratio, strongest proportions, the strongest orientation. I mean, because most of the material is furthest away from the axis. So that's the y axis this way. That's the x axis. As you can see, this section is actually doubly symmetric because it's symmetrical about y, symmetrical about x. TF is the thickness of the flange, which is that one, same as that one. D is the depth of the section overall. And this section is 203 by 203 by 52 UC in the question. The width of the section B is the width of the section, D is the depth of the section, TW is the thickness of the web, which is that little dimension in there. I haven't shown the root radiuses where the web meets the flanges because it's too small to show it. Not really worth drawing that out. So the first thing to do, so it says, check whether this UC section will buckle locally under the axial compression load. The first thing to do is to check the basic material property using the grade of steel given there. It said in the question that the grade of steel is 275. So the equation that you need to use is this one: epsilon equals 275 divided by py to the power of 0.5. So in this case, epsilon is 275 divided by 275 square root, and that is equal to 1. So that's nice and easy. Epsilon is 1. So you might have 275 over 355, and then epsilon will be less than 1. But in this case, it's just nice and simple. 275 is 0.5. It is suggested that a 203 by 203 52 UC section of 275 steel be used for this column. So the first thing, so we found out that epsilon is 1. That should in there. So the second thing to do is check the slenderness of the compression flange. So the limits for this are that basically it says will it buckle. So what you need to do is find out whether it will buckle if the slenderness of the flange if the flange is slender, then it will buckle. If the flange is plastic, then the entire section will fail as a plastic hinge. The whole section will reach the plastic yield stress like this one. There's a separate. I just took this from, not breaking the copyright, but structuralguide.com, design of the universal beam classification of section as per BS 5950. Well, it's actually, we're looking at column design, but I think it's still applicable. Yeah, so class 1 sections, plastic, class 2 section, compact section, class 3 section is semi-compact, class 4 is slender section. So you don't need to write all this down in the exam, but I'm just trying to explain how I get the answer. So as on this side, class 2 and 1, the section for compact and plastic sections, the yield strength will be reached throughout the section before the web buckles. With semi-compact, I think only on the outside extremes of the section that will get it, and on the on slender sections the web will buckle before it gets to the plastic yield stress. So going back to our design, so check the slenderness limits of the compression flanges. This is check the slenderness for actually loaded members. So it's in here it is. It's in the design guide for BS 5950 anyway. Yeah. So just going back to the video. So check the slenderness of the compression flange. So for plastic class 1, the limits are B divided by 2 times T is equal to or less than 9 epsilon. So epsilon in this case is 1. So for plastic class 1 sections, it's got to be 9 or less. For compact section class 2, it's got to be 10 or less. And for semi-compact section, it's going to be class 3, 15 or less. And when I said 9, 10 and 15, I mean the ratio of B, which is the width of the section, which is the width of the flange, divided by the 2 times the thickness of the flange. So basically, as on my little diagram that I've done here, this is a part section. So this is the top flange, not to scale because it should be a bit thicker than that, but this is the thickness of the flange here. This is B over 2, which is half the width, which is half the width of the flange. So the ratio B divided by 2 divided by T must be equal to or less than 9 for class 1 sections, 10 for compact sections. It just basically means that if the web is slender, it's going to be this long, and if the web is shorter, it's going to be stiffer, because it's like a cantilever basically, isn't it? So this will be like with a massive ratio like this, if this is just a free arm where I'm holding it like this, whereas if I hold it here, obviously this is a lower ratio of width to thickness. So it basically means that it's slender the longer that free end of the longer the free end of the cantilever is of the flange basically. So in this case, B, the width is 204.3 millimeters. Thickness of the flange is 12.5. Therefore, B divided by 2 times TF equals 204.3 divided by 2 times 12.5 equals 204.3 over 25 equals 8.179, which is just less than 9. Oh, it's epsilon as well, so it's 8.172 times 1, so it's less than 9. As this is less than 9 in the steel grade, this section shape for this compression flange is plastic. So for this column, 203 203.57, standard 275. I mean, I think basically, if the material is stronger, then there's more chance for it to buckle. So if I had 1,000, like in theory, you can't get that, but if you had P weight equals 1,000, then 275, then obviously epsilon is going to be making that 9. That 9 could be lower because the web will buckle first before it yields with the stress. So the stronger the section, the lower the value of epsilon. So just be aware of it, basically. Just be aware of that's how it works. So on this occasion, 203 by 203 times 52, ratio is 8.179. That's B divided by 2 times the thickness of the flange. This is less than 9 times 1, so that's okay. So this section is the classification of the flange for this section is plastic, so it will fail by plastic yield. Then the second thing to do is to check the slenderness of the web. Remember, it is suggested that a 203 times 203 times 52 universal column section 275 still be used for this column. So plastic class 1 limits now this is much bigger. This is slenderness of the web. Now I think I've got this right. Plastic class limits, this 80 must be the ratio of D divided by TW must be equal to less than 80 epsilon. Just show you, just put that in there. Should have done that before. So basically I've drawn it here. I just need to zoom out a bit. Yeah, 110 maybe. Oops, zoom out a little bit. So here's a section. D is the depth of the section between the fillets in the corners connected to the flanges. So the distance between the so not including any curved bits of the web. This is D, and TW is the thickness of the web. So the ratio between the depth of the section, or the longest part of the web, divided by the thinnest part of the web. So that has to be less than 80 epsilon for plastic class 1, for class 2 compact 2, class 2 compact, less than, the ratio must be less than 100 epsilon, and for semi-compact it must be less than 120, otherwise it's slender. So so D divided by TW, it must be equal to or less than 80 for class 1 plastic section. In this case, D equals 160.8, TW equals 7.9. I got that from the tables, therefore D divided by TW, 160.8 divided by 7.9 was 20.35443037 blah blah blah, which is less than 80, which is less than 80 epsilon. As this is less than 80 epsilon, in the steel grade, the section shape, in this section shape for compression web is plastic class 1. So that basically means in both cases, for the web and for the flange, the section is plastic. So based on the section data, classification of unit beam sections can be done. Similarly, other sections having actual loads can be classified as given in Table 11 of 5 BS 5950 2000. So I think I'm right, and what I've just done on this video, this is another reason why I'm doing this video separately, but I think it's correct. Just to make sure, there is some notes. So it was just reading about that the ratio of the flange to be plastic will change basically depending on the actual load, but I'm just going to have another look at that. But for now, I think this is all correct, but please correct me if I'm wrong, if this is not right. Refer to my next new videos on column design, maybe more complicated for columns with actual load. You know these ratios, this might not be 100% correct, so please come back and have another look. As far as I'm aware at this time, that is 80. I think definitely think the compression flange is right, whatever, because it has to be less than 9 epsilon for the flange. 9 epsilon plastic, 10 epsilon compact, 15 epsilon semi-compact, otherwise it's slender. So I just need to double check the slenderness of the web ratios. At the moment I think plastic 80 epsilon, compact is 100 epsilon, and semi-compact is 120. That's it for video number 2. Hope you found this information useful, and I will update this. And please like this video, please subscribe to the channel, and please so I can make more videos, and please donate if you can, and then I can do some more videos on this structural analysis. Thanks for watching.